Welcome back. In the last session, we had seen active region conditions and the first circuit of DC analysis, and then I just explained VBB, RB, RC, and then transistor beta. This is what is the configuration for DC circuit, and we are trying to keep the transistor in active region. Then we applied VBB, RB, then we are getting IB, then we are getting IC, then we are choosing RC to get the drop whatever you want, let us say 5 volt. Then transistor is ready for the amplification because it is in active region. When transistor is ready for the amplification, then applying the AC signal to amplify, that is what is applied. Then the small VBE is giving small IB, the small IB is giving small IC, then the drop across RC, and then ultimately the output voltage, which is what is swinging about the DC voltage. That is what your operating point. Okay, done. But let us say this is what is Q1, a different operating point. Now Q2, a different operating point when VC is equal to 2 volt. Then if you go ahead with the swing, whatever you are expecting, this is what is my input swing and then I'm getting this output swing, then you are seeing distortion. But without having the distortion, what to do? The next solution, right? That is what I'm trying to explain. Okay. Now I think this is already written in the last session. If you resume the video and then write all these things. Now the continuation part, I told you the next one, the solution is, because this is not acceptable, distortion is not acceptable. Whatever audio signal, let us say audio amplifier, whatever audio signal or voice signal I am giving, there should not be any distortion. Whatever I am giving, I want loud amplitude, and that is what is given to loudspeaker, therefore you get huge sound. I don't want to see any distortion, right? No clipping. Therefore now the same operating point Q2 only, but the solution. Therefore now if you see here, this is what is 0.2 volt, approximately 0. But my VCE, this is what is my VCE, that is what is 2 volt. Then what to do? We have to apply the input. Therefore don't apply this much input. Now decrease the input. When you decrease the input, apply the small signal. When you apply the small signal, anyway we are going to apply small signal only. When you apply the small signal, then I don't want this much gain, this much amplitude, right? Therefore what you get, let us say, then you may get like this. Therefore there is no clipping. For your understanding, let me take, therefore for your understanding, what is this peak to peak? Let us say the peak to peak, right? This is what is around 8 volt. Okay. And now let us say I am giving here peak to peak, input peak to peak is 0.8 volt. Let us say I am giving input peak to peak 0.8 volt. 80 millivolt. Therefore this is what is the input peak to peak. Let us say case 1, this is what is the case, I am giving 80 millivolt peak to peak. And let us say the gain of the amplifier, the voltage gain is 100. Okay. Then tell me what we get here. The input is 80 millivolt peak to peak. Input is 80 millivolt peak to peak. This is what your input, small signal. Then let us say gain, voltage gain AV is equal to 100. Then what you get? V0 is equal to 100 into 80. What is 100 into 80? 80 into 8000 milli, which is 8 volt peak to peak. Therefore this is 80 millivolt peak to peak. With the gain of 100 you will get 8 volt peak to peak. That is what we got, right? Therefore your gain is 100 only. Now coming to this is what is operating point 1. Now this is operating point 2, right? Now if this is what is the case, right, this is not acceptable. But now here what is this? Your input is not changed. What is your input? Input is 80 millivolt peak to peak. But now what are we getting? My gain AV is equal to 100. I'm just taking magnitude because we have minus 100. Then what you get? I'm expecting V0 to be equal to 8 volt peak to peak. I'm expecting output to be 8 volt peak to peak. Let us say this is what is 2. Then definitely I'm expecting this to be what? This to be 6 volt here. This is 6 volt. And now 2 minus 4, I'm expecting this to be minus 2 volt. Then only 6 minus of minus 2, you will get what? 8 volt peak to peak. But my DC voltage is 2, my operating point is at 2, maximum swing, negative swing I can get is only 2, but I am expecting 4, therefore total 8, therefore we are seeing distortion because the minimum voltage what I can get is 0 or 0.2, therefore it is almost 0. which is not acceptable. Now what to do without affecting your gain? Now what I'm saying, don't apply. Let us say I'm trying to get maximum 4 volt, right? Then what I'm doing, instead of 80 millivolt, can I apply 40 millivolt? Let us say Vi is now 40 millivolt peak to peak. When I say 40 millivolt peak to peak, now the gain AV is equal to mod AV is equal to 100. Don't write. Now my gain mod AV is equal to 100. Okay. Mod AV is equal to 100. Okay. Then tell me what you will get. 40 milli into 100. You will get, this is what is my V naught. 4 volt peak to peak. You will get 4 volt peak to peak. But can you get 4 volt peak to peak at the output? Yes, you can get 4 volt peak to peak, because 2 and then this is what is nothing but 4 volt and this is approximately 0 volt. That is what you can get. Then what is your peak to peak? Now your peak to peak is 4 volt. Now no distortion. Therefore this is acceptable. There is no distortion. Therefore what to do? But remember, gain is 100 only. I am not changing the gain. You may think that gain is changed. With respect to AC analysis, your gain is not changed. But you know what happened? By applying small signal or reduce the signal at the input, we are getting at the output which is not having any clipping, or which is not having any distortion. That is what it is. Okay. Therefore, remember, once the operating point is fixed, you can take any operating point, right? But you have to analyze for what input peak to peak you are going to apply, therefore what output peak to peak you are expecting, because you know the gain of the amplifier. If you know the gain of the amplifier, then if you know the input peak to peak what you are giving, then definitely you know what is the output peak to peak you can get. If you know what is the output peak to peak you can get, then if you choose 2 volt, the maximum output peak to peak you can get is nothing but 4 volt only, not more than that. If you try to get more than that, you see clipping. Okay, then we have to choose the output operating point such that there is no clipping, or you reduce your input peak to peak. If you reduce your input peak to peak, then even though your operating point is at 2, then you will not see any distortion, right? But what it may be, if input peak to peak is fixed, my operating point is fixed, then always I will get my AC signal about the operating point what you set. But whatever operating point is set, after all fixes, where the design is over, design is done, releasing into market. But if the operating point, whatever you set, if temperature changes, whatever 2 you kept, let us say that is going down, then you see clipping, right? Which is not acceptable, which you cannot do. Once the design is over, before the design, whatever you want, you can do it. Remember, before the design, whatever you want, you can do it. But once the design is over and releasing to market, but temperature is not in your control. Let us say temperature is changing and time is not in your control. Your time is also changing. Therefore, whatever operating point you set, that operating point should be stable. If that operating point is not stable, then you may see distortion which is not in your control. You understand the point? That's why we want Q point stability. Not only keeping the transistor in a required region, which is active region, we need to, after keeping the transistor in a required region, that operating point, whatever you are setting, that should be stable. If that is not stable, remember, before the design, after the design, you will see distortion which is not acceptable at all, right? Let's see. Therefore, that is the reason why after this we are going to see the limitation of the circuit. The limitation of the circuit is your Q point is not stable. Even they are keeping at 2 and then leave it and then release into market, but because of temperature variations and all, it is not stable. Why it is not stable? That part I will explain. Okay, take this. But remember here, for your understanding, I just applied AC signal directly on top of DC signal. But practically we will not have like this. Practically we will not have like this. Practically we need to couple the external AC signal on top of the DC signal what you set by your biasing circuit. Okay, those things I'll explain. DC plus AC. This is only DC analysis. Just to explain, just to understand the meaning of Q point stability. If Q point is not stable, what will happen to the AC signal? I just took AC signal on top of DC signal for your understanding. But ultimately, this is what is the coupling. Equivalently, you can take the coupling DC to AC coupling like this. But practically, how will you couple the AC signal on top of DC? That part I'll explain. Just wait for some time. Then after completing DC analysis, anyway, you are going to see DC plus AC. There you will understand. Okay. Therefore, what is the observation? Purpose of DC analysis is to keep the transistor in active region. After keeping the transistor in active region, whatever operating point which is what is set, that should be stable. If that is not stable, you will see distortion. Okay. Once the design is done, it should be stable. But before the design, whatever, wherever you want to apply or operate your transistor, output voltage and output current, you can keep it. I think you have written already these two in the last session itself. Only the extra is this only. Okay, after this, write down observations. 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 First point. First point. By choosing capital VBB, comma capital RB, by choosing capital VBB, comma capital RB, comma beta, comma beta and beta, sorry, not comma and beta. By choosing capital VBB, comma capital RB and beta, we can get required capital IC, we can get required capital IC at the output, required capital IC at the output, in bracket DC bias current, in bracket DC bias current, DC bias current, dot. After required IC, after getting required IC, capital IC, after getting required capital IC, after getting required capital IC, comma, by choosing RC, by choosing RC, we can get required capital VCE, we can get required capital VCE, we can get required capital VCE, in bracket DC bias voltage, in bracket DC bias voltage, in bracket DC bias voltage. dot where, write down continuation, where the required VCE, where the required VCE, where the required VCE is greater than or equal to 0.2, where the required VCE is greater than or equal to 0.2, where the required VCE is greater than or equal to 0.2, to keep the transistor in active region, where the required VCE is greater than or equal to 0.2, to keep the transistor in active region, to keep the transistor in active region, to keep the transistor in active region, dot. The last point, therefore output bias voltage, capital VCE, therefore output bias voltage capital VCE, therefore output bias voltage capital VCE and output bias current capital IC, and output bias current capital IC, and output bias current capital IC, output bias current capital IC gives you a define output DC bias current IC defines operating point Q, define operating point Q, define operating point Q. You can write Q like VCE comma IC. Therefore, whatever DC bias voltage you got and DC bias current you got, this is what is called as operating point. That is what I need. That is what I want to explain. Therefore, operating point Q, VCE comma IC. Now, conclusion, that is observation, conclusion. Write down conclusion. The Q point should be stable. The Q point means output voltage comma output current. Okay. The Q point should be stable. The Q point should be stable. The Q point should be stable to do not see any distortion. To do not see any distortion. The Q point should be stable to do not see any distortion. Okay. Now let's see what is the Q point stability for this. Okay. Write down Q point stability. Write down Q point stability for your circuit. Q point stability. Okay. Now I don't need all these things. Now you understood what is Q point stability, what is Q point. Just to explain that, I just took DC point, DC voltage, and then on top of that AC signal. Okay. Now I can speak only with respect to DC signals. Okay. Now you have to draw once again. Don't disturb the original circuit. Now draw the once again without any AC quantities, only DC quantities. Okay. Let me erase all these things. Please draw once again the circuit without representing any AC signal, only DC signals. Okay. Therefore assume that we have chosen VC is equal to 5 volt. Okay, we have chosen VC is equal to, let us say, 5 volt. Maybe for your understanding, I am just taking one example. Let us say IC is equal to 1 milliampere, and let us say RC is equal to 5 kilo ohm. Therefore now tell me, if IC is equal to 1 milliampere, right, 1 milli into 5k, 5 volt. Therefore what is the drop across RC? 5 volt. Then what is the drop across the transistor output? 5 volt. Out of 10, 5 is gone here and then 5 here. But how are we getting 1 milliampere? That is because of transistor beta and then input current. Therefore what should be IB? You can say IC by beta. Let us say beta is 100, then I want 10 microampere. To get 10 microampere, choose RB, VBB such that you get 10 microampere. Simple. The design is simple. You can choose VBB, RB such that whatever IB you want, you can get it. After getting IB, if you know beta, then we can get IC. After knowing IC, choose RC to get drop across RC, whatever you want. Let us say 5 volt here, exactly midpoint of rail to rail, then you can get 5 volt. Okay? I'm just taking one example. Now, therefore what is your operating point? Your operating point is nothing but, in this example, your Q is nothing but what? 5 volt comma 1 milliampere. Therefore, your output voltage is 5 volt and your current is 1 milliampere. Okay? This is what your operating point. Therefore, whatever operating point you set, right? Therefore, can I say your VBB fixed? Fixed. RB fixed. IB fixed. IC fixed. VCE fixed. That is what we are getting. We are trying to get Q point fixed. Then I'll explain Q point stability. Okay, you draw that. Okay, Q point stability. Done? Now, wait. See, in the case of DC analysis, always we try to, I gave the procedure also, right, to solve the problems. The procedure is, whatever circuit which is what is given, right, if that is related to DC analysis, we have to deal with either input KVL, output KVL or device equation, right? Input KVL is known to you, output KVL is also known to you, and then device equation is also known to you. Therefore, what is device equation? Your device equation IC, we know that IC is equal to beta into IB plus 1 plus beta into IC naught, right? Now, if you see, therefore tell me what is your input KVL. If you take input KVL, VBB is equal to drop across RB plus drop across input transistor, which is VBE. Then from this I can get IB. Therefore, what is IB? Therefore, IB is equal to VBB minus VBE divided by RB, right? Now, do you know VBB? Yes, that is in your hand. That is your power supply, input power supply. Do you know VBE? Yes, we want VBE to be 0.7, greater than or equal to 0.7. Then only transistor will be in active region. Therefore, we know you can take typically 0.7, approximately 0.7, strictly speaking 0.7 to 0.75. But even if you take 0.7 also, that is fine. Error will not be much. Therefore, VBB is known to you. Let us say 5. VBE is also known to you. Let us say 0.7. 5 minus 0.7, 4.3 divided by, let us say RB 100 kilo ohm. Then let us say we are getting IB in the order of tens of microampere. Once you get tens of microampere, that is what your IB. Now, I want to know what is IC. That we know the equation, right? Remember, input to output, the job of converting input current to output current is your transistor only, because it is current control current source. Your primary relationship output to input is nothing but output current to input current, which is current control current source action. Therefore, IC is equal to beta into IB plus 1 plus beta into IC naught, which you already derived, right? Therefore, you know already IB from input KVL, and you know IC from the transistor relation, which is nothing but IC is equal to beta into IB plus 1 plus beta into IC naught. And once you know IC, can't you find, already IC is known to you. Now you need to find VCE only. How to find VCE? By applying output KVL. Therefore, what is output KVL? This is input KVL. And if you write output KVL, therefore what is output KVL? Your VCE, or after output KVL, what you get? IC is equal to drop across this resistor divided by RC. Then the same current is flowing, in series current is constant. VCC minus, out of VCC, VCE is dropped, and VC is also known to you. Whatever VC you want, you can take it, divided by RC. Therefore, you know IC, sorry, this is what is our IC. Now I want VCE basically. Therefore, what is VCE? VCE is equal to VCC minus IC into RC. Therefore, tell me, you know IB, you know beta, you know IC from this, and you know drop across RC, then we can find IC over. Now the question is here, let us say VBB is fixed, RB is fixed, right? Then your RC is fixed, right? Everything, your power supply is also fixed. Therefore, everything is fixed. But now we need to have IC to IB or IC to be fixed if IB is fixed. That is what we need, right? And IC to be fixed if beta is fixed. And IC to be fixed if temperature is changing. But practically, you know, your IC is function of all three parameters. Therefore, your function of reverse saturation current, the reverse saturation current is due to reverse bias PN junction rate. What we have, that is nothing but a collector junction, which I explained already, right? Therefore, it is depending on reverse saturation current. In turn, the reverse saturation current is depending on temperature. What it may be? IC naught, and it is also depending on IB. IB means what? You may say this is IB, right? You may say IB is constant. But remember, IB is constant if VBG is constant, right? Because VBB, RB, they are fixed. Let us say, if VBG is constant, then IB is constant. But you know, VBG is nothing but V gamma, the cut-in voltage. The cut-in voltage will change with respect to temperature, right? I already explained that point. The minimum voltage required to cross the majority carriers from the either parts of the PN junction or through the PN junction or through the barrier, because it has a barrier, right? If temperature increases, the majority carriers from P and N, they get extra energy, therefore they can cross with minimum voltage. Therefore, the depletion region basically, indirectly, effectively, the barrier potential is decreasing or V gamma is decreasing. If V gamma decreases or when VBG decreases, your IB will increase. Okay. Therefore, it is also depending on IB and it is also depending on beta. What is beta? HFE. I told you, right? Beta is nothing but HFE. Your HFE is also a function of temperature. Therefore, ultimately, all these three are depending on temperature. When all these three are depending on temperature, if temperature rises, then your IC naught increases, your IB will increase, your beta will increase, your IC will increase, which is unexpected, which we don't want, because I want IC to be fixed. Remember, if IC is changing, drop across RC will change, then your VCE will change. Basically, your Q point is not stable, your Q point is changing in this circuit, right? But whatever I explain now, let me explain through flowchart. Just listen here. Now, if temperature increases, if temperature increases, then can I say your reverse saturation current IC naught, that is increasing? When IC naught is increasing, what about your IB? Your IB is also increasing. Sorry, when temperature increases, your IB is increasing. When temperature is increasing, your beta is also increasing. All three are increasing your IC. Therefore, your IC is increasing because of all three. When IC is increasing, then tell me the same current is flowing through the transistor. Then the power dissipation across the transistor increases. Therefore, let us say the power dissipation at the collector junction is equal to IC square into R of the collector junction. Right? When that is increasing, your power dissipation increases. When the power dissipation at the collector junction is increasing, the heat energy whatever you are having, we are getting from the collector junction, that is increasing. When the heat energy is increasing, if that heat energy is not dissipated into the environment safely, right, then you will see accumulation of heat energy. When there is accumulation of heat energy, then your temperature will be raised. When temperature is raised, then again all three parameters will be increased. Then ultimately your IC will increase. If IC is increasing, power will increase further, heat energy will increase further, then heat accumulation is there. If that is there, and your temperature also will be raised further, then ultimately your IC is increasing, which is worst case. Then when IC is increasing, then you'll get maximum drop across RC, then maximum 10 you get here, then VC will be minimum, then the Q point will be moving towards the saturation region. It will enter into saturation region. Therefore, what will happen? Q point moves towards saturation region if temperature increases, towards saturation region. And remember, this is what is called thermal runaway. This is what is called thermal runaway. Therefore, your Q point is not stable for DC circuit, in this circuit. But what is the name of the circuit? I didn't give the name of the circuit, I just told that DC circuit, right? But what is the name of the circuit? And one more point, just listen. Temperature is increasing, IC is increasing, Q point is moving, right? Therefore, this is what is called thermal runaway. Remember, this is true only when there is an accumulation of heat energy. Let us say IC is increasing due to temperature. Okay. Now, power dissipation is increasing. Then the heat energy whatever you are getting, right, that is increasing. If that heat energy whatever which is increased, if that is what is dissipated safely into the environment, if there is no heat energy accumulation, then your temperature will not rise. That is important point. Always we will not see temperature rise, provided whatever heat energy which you are getting from the transistor, if that is not going into the environment safely, if there is no heat sink, let us say, where the heat sink is not taking out the heat energy what you have, then there is a delta between the heat energy at the transistor and the heat energy in the environment. If there is a delta, then definitely, right, this will be what you call, not the delta, I can say if the heat energy is increasing, because it is not safely dissipating into the environment, then you will get temperature that will increase, then you will get temperature delta. When the temperature delta is there, more heat energy is trying to transfer, but whatever it may be, the heat, if it is coming continuously, then heat accumulation will be there. If heat energy is transferred, then there is no heat accumulation. If there is no heat accumulation, then your temperature will be constant. Okay? But remember, this is what is pessimistic case, where if heat energy is increasing, if that is not accumulating, if that is accumulating, then only temperature increases in turn, and it is like a positive feedback, then your Q point will be moving towards the saturation region, and that is what is called thermal runaway. Okay, take this, then I'll explain the name of the circuit. I didn't explain the name of the circuit, or I didn't give the name of the circuit, right? After this I'll give you the name of the circuit. Okay, take it. I'll explain little bit about why IC0 is increasing with respect to temperature, then how IB is increasing with respect to temperature, and then we know that beta increases with respect to temperature because that is transistor H parameter, then if it increases with respect to temperature. Okay, I can explain IC0 change with respect to temperature, IB change with respect to temperature. Okay, actually there are few problems related to that IB change with respect to temperature, or the PN junction level current change with respect to temperature because of cut-in voltage change. I think if you solve those problems, then it is so clear. Okay, maybe I'll try to explain, or I'll try to give now only, therefore you'll understand that. Okay. I'll give you 30 more seconds. Over. Now let me explain the name of the circuit. Till now we didn't see the name of the circuit, right? Okay. Can anyone think about correction? Means I don't want to see the change in the Q point. Because of temperature, your IC is changing. If IC is changing, your Q point is changing, right? Now, just listen. I'm just explaining the solution part qualitatively, but whether we can implement it practically or not, that is later. Let's see qualitatively. What is that? Let us say if temperature is increasing, ultimately your IC is increasing. When IC is increasing, your VC is changing, right? Let us say if temperature is increasing, right, because of IC, if I can decrease my VBE, how much is the increment in IC due to temperature? If I decrease my VBE such that IB will decrease, therefore IC will decrease. If IC is compensated by changing VBE, let us say, then problem is over. What I am saying, and let us say VBE, your input IB or input IC, right? Everything is constant, or what will be IC? I am expected to be constant, right? Now due to temperature IC is increasing, then decrease VBE, then IB will decrease, IC will decrease. Therefore indirectly we are compensating IC change because of by changing VBE. Therefore whatever VBE you are applying or you are getting through VBB RB, right? And that VBE if you can adjust to control your IC, then problem is over. Then you will not see Q point movement. Then Q point will be almost stable, right? Now, but in this case, your VBE is fixed because of VBB and then RB. Therefore, your bias voltage VBB is fixed, RB is fixed, RC is fixed. Because of fixed bias, we are seeing Q point stability. We don't want fixed bias. We don't want fixed bias. I want variable bias or automatic bias, or I can say self bias. I want automatic bias such that if there is a change in IC, then change VBE automatically, but not with fixed voltage. Automatically the VBE has to be adjusted such that your IC will be adjusted to the expected value, which is what is 1 milliampere. Then I can say, then you will get Q point stability. Therefore, to get Q point stability, we don't want fixed bias. We want Automatic bias or self bias or on its own it has to correct the voltage such that your Q point will be stable. Therefore, the name of the circuit is nothing but fixed bias circuit. Your bias is fixed but temperature compensation is not there. Therefore, your Q point is not stable. This is what is your fixed bias circuit. The name of the circuit is fixed bias circuit. Your bias is fixed, but I don't want fixed bias. To compensate the change in IC, I want to change VBE or I want to have variable bias or automatic bias or self bias. Therefore, you will get compensation, then you can make IC stable. Write down the name fixed bias circuit. Over. Therefore, what is the limitation? Limitation of fixed bias circuit. Write down limitation. Limitation is nothing but Q point is not stable. Because Q point is not stable, you may expect thermal runaway. Q point is not stable, therefore thermal runaway can be expected. If temperature changes too much, can be expected. If temperature changes too much. Okay. Now, I'll explain change in IC0 with respect to temperature, change in IB with respect to temperature. Let me complete DC analysis part, then I'll come to IC0 and then IB. Okay. Means how are they controlled by temperature. Now write down the second circuit. Therefore, what is the limitation of the circuit? Remember, we want two things only from DC analysis. Number one, we need to keep the transistor in active region. Yes, I am able to keep the transistor in active region, but Q point is not stable. After keeping the transistor in active region, if you release into market, the Q point is not stable because of temperature. Therefore, we are seeing Q point stability issue. Then nobody will agree for that. It is not acceptable. We want Q point stability due to temperature. Therefore, for that we need to improve the stability. Then what to do? I just told you a theory that if you bias or the bias whatever you are applying, if that is what is automatic or self bias circuit, right? Then I can say it will be controlled, or I can say Q point will be stable, right? But you know how to get the VBE bias automatic, or from system perspective how to improve stability, not only voltage gain stability. Remember, when I speak about stability of anything, if you want to improve stability of anything in that way, always the technique is negative feedback. If you want to improve the stability, we have to apply negative feedback. Therefore, negative feedback will be incorporated to the circuit such that you will get stability. You understand the point? Therefore, before going to the next circuit, actually this is not practical fixed bias circuit. There is another circuit, because tell me how many power supplies you want for this. You want output power supply VCC and input power supply VBB, right? Therefore, I want to use single power supply. I want to use single power supply for both input and output to bias the transistor, right? Therefore, you write down practical fixed bias circuit. Practical where I want to use only single power supply. Practical fixed bias circuit. With that, I can say fixed bias circuit is over, and we are having two more circuits. If that is done, I can say DC analysis is over. Then I will close the session. Write down practical fixed bias circuit. Practical fixed bias circuit. with only one supply. You know, instead of VBB, you take VCC as your input. That's it. Problem is solved. Now we can have only single power supply. This is collector, base, emitter. This is what your practical, because I want to use only single power supply. I don't want VBB, VCC, two supplies, right? I want to use single power supply. Instead of VBB, indirectly we used VCC. Then you have to choose, or you have to change RB such that whatever IB you want, you can get it. Okay? This is what is our IB, and this is what is going to give you IE, and this is what is going to give you VCE. Right? Then your operating point is VCE comma IC. This is what is your operating point. Right? Let me stop this session now. Maybe if you want, you can resume the video. We have 1 more minute. If you can complete that in 1 more minute, that is done. Anyway, I'll explain a little bit about this in the next session. Thank you.